Let's welcome John Abatzoglou, Dr. John Abatzoglou, currently an associate professor at the University of Idaho in the Department of Geography. His research interests include improving our understanding of the past, present, and future climate of the American West, as well as their impacts to the people and the natural resources of the region, including water resources, wildfire, and ag. His Applied Climate Science Lab at the University of Idaho contributes to climate science research, as well as a number of data sets and web-based tools used by researchers and decision makers. Let's welcome John.
Should we just go straight to lunch? I'm hungry now. Show of hands for those who are ready to see winter be over. Who's not raising their hand up? Okay, so rest assured, next week, February 2nd, Groundhog Day, I have a plan to convince the groundhog not to see a shadow so we can end this winter and get on with spring. As we all know, over the past 6 weeks or so, the Northwest has seen its coldest bout of temperatures in the past 25 to 40 years. Boise, Idaho reported its greatest snow depth on record earlier this month, and as we probably know, daily life in the gorge was held at a standstill last week after about 2 to 3 inches of freezing rain. You can just take a look at all the down debris out there and figure that it was a significant event. This is climate variability. We expect climate variability to continue in a changing climate. And what makes this winter particularly striking is just how cold it has been in contrast to the relatively mild winters that we've seen over the past few years and realistically the past few decades. We've seen winter temperatures like this before, but we have to go back, several generations to actually have seen them more frequently. Now, last week, NOAA and NASA officially announced 2016 as the warmest year in the instrumental record, taking the title from 2015 that took the title from 2014. If you look at the data here, this is the data from NASA, about 1 degree Celsius above normal for the globe in 2016. And what we've seen is that 16 of the 17 warmest years on record globally have happened since 2000. This is what a warming climate looks like. This is what the data tells us. This is what the science tells us. Now, very few of us can appreciate the relevancy of global numbers like this. 1 degree Celsius globally, what does that mean to you or I? It's a little bit difficult to get, or wrap our brains around. And even the term global climate change is a little bit challenging for us to sort of really respond to. And that's fair. We all live in and are more intimately connected to weather and climate at our front doorstep and in our region. And so with my time this morning, what I'd like to do is walk you through what we know about observed changes in climate and water resources across the broader Northwest. I'm giving you a survey of that. And also talk about what the future is in terms of climate and water in our region. And I'd like to basically put forth a hypothesis that climate change could actually load the dice for the region to experience both more frequent drought and more frequent bouts of heavy precipitation. So from an outsider's perspective, the Northwest is very rich in water. It's known for its lush forests, incessant precipitation, and the concept of Northwest drought to many seems like an oxymoron, right? But it's useful to sort of think about the geography of climate and water resources across the region. And when we do that, we can look at a map something like this, right, or temperature, and we see that there are tremendous gradients in climate and water resources. And these are gradients that are sort of telling us where precipitation falls, right? Where we can cultivate crops, where our forests can grow, where we recreate. These things actually end up influencing our economy and our culture. So we are intimately connected with climate and water in the Northwest. It actually shapes us to a pretty good degree. And the concept of the haves and have-nots of water, right? You can look at it on this map here. About a third of the combined lands in Idaho, Oregon, and Washington receive less than 15 inches of precipitation a year, and that hardly qualifies as being lush. And these differences between when precipitation falls and where precipitation falls are made additionally even more complicated due to the fact that we have seasonal asymmetry in precipitation. Namely, precipitation typically falls in the cool season, typically gets utilized in the warm season. Now, fortunately, we have these things in our mountains these frozen reservoirs called snowpack. That helps us cope with this seasonal asymmetry. Right? So we have this reliable way of basically storing water in mountain snowpack, having that melt in the spring to feed our rivers, for us to feed our crops during the dry season when we otherwise have moisture shortfalls. So we talked about, you heard earlier this morning about the water year of 2014, 2015, and I'll get into that as it's potentially sort of a trial run for what climate change might look like more frequently across the Northwest. And it does sort of show us a couple things. One is that the Northwest can actually have droughts, and we do see impacts from droughts. Fortunately, we've seen a recovery. There's been a widespread drought abatement across the Northwest over the past 15 months or so due to a healthy water year last year and a decent start to the present water year. And realistically, from a broader water resources perspective, the Northwest has been relatively well off over the past half century. And by that, I mean that we have avoided protracted drought across the area. We've seen single-year droughts, maybe a couple-year droughts. But if we look back at the longer-term record, before we had widespread sort of irrigation across the region, in the 20s and 30s we had multi-decadal drought. We can look at our neighbors to the south. In California, the Southwest. The Southwest has basically been in a state of drought since 2000. Okay. So we've been pretty fortunate. It's part of the climate system. It could happen again. At the same time, we have begun to see impacts from climate across the region. And those impacts have shaped water resources and ecology. So we'll take, for example, the 1 degree Celsius documented warming that we've seen across the area, most of that occurring over the past half century. Question is, what is 1 degree Celsius worth to you? If I want to be able to control the thermostat in this room and turn the temperature up by 1 degree Celsius, maybe one person would take their jacket off. Probably wouldn't notice the difference. It does have an impact on climate, though. So we'll take something simple. If you warm the temperature up by about 1 degree Celsius, that roughly translates into a 500-foot increase in the freezing level, or the snow level. Okay? And what that ends up resulting in is more precipitation falling as rain, less as snow. Less of that precipitation is stored in mountain snowpack, more of it runs off earlier in the year. Okay, and that leads us to perhaps the most renowned hallmark indicator of climate change across the American West, and that is the decline in spring snowpack across our mountains. We don't see temperature, okay, but we can observe, and we can see snowpack. And this is pretty widespread, both across the U.S. and up into Canada as well. And as more of that precipitation falls as rain, less as snow, more of that snow melt runs off earlier in the year. There's simply less water to run off in the summer months. And so a consequence of the changes in hydrology tied to climate in the Northwest is that we have a reduction in summer flow. So that was noted earlier today, both in terms of a stream flow perspective, also running into moisture shortfalls for dry land farming heading into the latter parts of summer. And along with this, we've also seen not only declines in overall flows in summer, we've also seen a greater incidence of these 7Q10 flows that have an implication for water quality. So particularly low flows that we might experience 1 out of every 10 years, sort of a weekly flow. And the story isn't in there, right? So the decrease in mountain snowpack, along with warming temperatures in summer, collectively act to hasten the rate at which fuels dry in our forests. That has increased the susceptibility of our forests to wildfire. And we've seen significant increases in fire, about an 8-fold increase in forest fire burned area across the western U.S. over the past 30 years. Climate change is contributing to that. So we've learned a lot just from observations, right? We've had observations. We have a pretty good observational network out there. And we've learned that our environment here in the Northwest is sensitive to climate variability and change. We're not immune to it. We may have a lot of water relative to some of our surrounding states, but we do have impacts. And we've seen these impacts occur with about a 1 degree Celsius warming, right? Now the reality is we look into the future and look at what the data tell us about the magnitude of climate change in the pipeline. We'll be lucky to avoid an additional 2 degrees of warming. And that is highlighting the importance of us to better understand what climate impacts are across the region and how we might be able to adapt to climate variability and change. And I should mention that a lot of the efforts to try to impact climate change, they can also improve our climate readiness to adapt to variability. So that might be something that we might want to move forward with in sort of proposing climate change plans. They're actually a way to cope with variability as well. So with that, I want to sort of move from talking about the past to talking about the future. And in order to do that, it's important to be transparent about what the science tells us about climate change, about things we know and things we don't know. And this is sort of, basically the state of the science in pictorial form. So the point being here is that we know quite a bit about climate change, implications for regional water resources, and impacts. And then there are things that we don't know quite well. These are knowledge gaps in the system, right? And through time, scientists are working to fill in these knowledge gaps, and we'll fill in some of these pieces of the puzzle. But the reality is that, like most sciences, there's always questions people are asking. There's always unknowns. And so these gaps here, to some people, might cloud what the future is going to look like in terms of climate, water resources for the region. Okay? They make it impossible to provide precise forecasts or projections of what's going to happen. So we can either deal with that uncertainty, use the uncertainty as a reason to not act, okay, or embrace it. But the picture is pretty clear, right? And the picture from climate science tells us that the Earth is warming, humans are the predominant cause, and that we have a substantially warmer future ahead of us. So climate scientists don't have the ability, like biologists, to understand how a certain experiment plays out. We can't simply basically colonize a bunch of planets, double CO2 on some planets, don't double CO2 on other planets. We just can't do this. It's not possible with Earth science, right? So to overcome the limitation, what we have to do is rely on numerical models, or best understanding of how the climate system works. Okay, and these are run by a number of different groups globally. And the point is that we don't have a single model to rely on to tell us what the future is going to look like. We have a collection, an ensemble of models. And that's probably a good thing, right? If we relied on one model and it was an outlier, it might be a little bit problematic. So one thing to think about when it comes to climate change is we have uncertainty. And what I'm presenting you here is basically a way to think about that uncertainty. And this looks like a figure I saw earlier today. This is basically showing us the projected changes in temperature averaged over the Northwest, right? Idaho, Washington, Oregon, Western Montana. Right, from a baseline, 20th century average. And the gray line is showing us sort of the models run over the historical period. They show us about a 1 degree Celsius warming. That's pretty much what we've seen. And then the future trajectories, there's uncertainty in there. That uncertainty comes from the models, right? Decadal variability. But there's two main things to point out. One is that all models show warming. Okay? And the magnitude of warming is substantially greater than what we've seen so far. I should mention that what you're looking at here in yellow and in red are two different pathways. So one thing that sort of clouds our ability to provide people with sort of what the future is going to look like is we don't know how humans are going to respond. We don't know how politics are going to respond. And so there's two different pathways here. One is a pathway where we basically continue our emissions, business as usual, as we've done for the past, say, 20 years or so. That basically follows this red trajectory, right? And under that trajectory, we see a warming in the region of about 10 degrees Fahrenheit. That's extremely transformative, right? Under what's called the reduced emissions pathway, and that pathway, if you have followed some of the treaties that have gone on in Paris, if we abide by the Paris treaties globally, not just the U.S., but globally, and continue efforts to reduce greenhouse gas emissions, we'll follow that trajectory. And we still see a lot of warming, but it's about half that rate by 2100. Another thing to point out here is you don't see much separation until the mid-21st century. So while there's a lot of uncertainty in terms of how climate might change, depending on models, depending on scenarios, what I'll do for the remainder of this talk is focus on the mid-21st century, and I'll just focus on the multi-model mean, right? I'm not going to look at the outliers, but I want to point that there are outliers. Now, how will climate change spatially across the Northwest, right? The Northwest obviously has a lot of spatial variability in climate by itself. One thing that we've been doing with support from the Northwest Climate Hub is taking a lot of the climate change projections that we've developed and actually converting them into a number of maps that can be easily accessed. So we'll talk a little bit more about this tomorrow as well, but this is basically showing here the changes in temperature across the Northwest, and you do see some variability here, less warming along the coast and inland. One thing that I'll point out here is that there are efforts to basically understand the spatial heterogeneity in the rates of warming and how precipitation is going to change, and these use regional models. And one thing that comes out of those regional models is that we end up seeing amplified rates of warming during the winter and spring in areas that go from snow cover to an absence of snow cover. Right, so that makes sense, right? If you were to get rid of all the snow cover out there on the landscape, you'd actually heat the landscape up quite a bit more. So this is a weather conference. We should talk about changes in precipitation, right? So unlike the changes in temperature, where you see pretty substantial increases, far more than the variability, the signature for precipitation is a bit more ambiguous. You see a lot of variability. Some models project declines, some models project increases. The lion's share of models actually project increases in precipitation in the annual mean for the Northwest. Right? These increases are pretty small, 5 to 10%. One question that I often get asked is, can't we get better models to provide us with some more information on how precipitation may change across the region? And the reality is that may not happen. We actually probably shouldn't bank on getting more precipitation across the region. That's uncertainty that we probably do need to embrace. One thing that I will point out here is if we look at how this changes seasonally, we end up seeing a bit stronger signal of increases in precipitation in the winter and decreases in the summer. So that basically is adding to the seasonal asymmetry that we currently have in the Northwest, with more precipitation in the winter, less in the summer, and that leads us to potential implications for water resources. Okay, so the implications for water resources in the Northwest with climate change: on one hand, we might have some evidence to suggest increases in precipitation. On the other hand, we have pretty robust evidence to suggest increases in temperature. So I have three basic messages to present here. The first one's pretty basic, right? And this follows basically what we've seen thus far. One thing we know with climate change, there will be some non-stationarity in how sort of hydrology responds to climate. But one thing that we know with certainty is that the freezing point of water isn't going to change. It's still going to be 0 degrees Celsius. I'm pretty confident with that one. So with warming, we should expect snow levels to rise, right? And we've already seen impacts across sort of the lower elevation watersheds in the Cascades and the Sierra Nevada. Warming should basically move that elevation of the freezing level uphill. And what that means is that some areas further into the Cascades in the northern Rockies will also start to see substantial reductions in the amount of precipitation being stored in mountain snowpack. On the other hand, if you're really, really high up and really, really cold, so the central mountains of Idaho, up into the Yellowstone area, if you're at a negative 10 degrees Celsius and you warm by 3 degrees Celsius, you're still below that 0 degrees Celsius threshold. So that's just some simple math. At least in February, the answer changes quite a bit as you head on. And so one thing that I heard this morning, and I think is pretty clear with what we've seen so far in terms of stream flow across the area, with warming, we expect more of the precipitation to fall as rain rather than snow. And so the monthly stream flows, the hydrographs should change, right? We should expect a little bit more of a flashier flow regime. More of the precipitation falling as rain will run off during the winter and spring. Right? That's indicated by the blue and the yellow, or the blue and orange curves here are the future projections. Black is the historical values. And then this particular simulation is shown for the Yakima River near Cle Elum. Historically, you've had this nice snowmelt pulse that happens in May, June, July, right, providing replenishing flows in the river. That is expected to drop off substantially, and you see much lower flows here in August and September. These, by the way, are all sort of unmanaged systems, so clearly there's other things that can be done. More drought. Okay. And I think we could probably have a conference for like a week on trying to define drought, and we'd probably actually end up more confused than when we started. There's lots of ways to define drought. My former postdoc advisor and mentor, Kelly Redmond, defined drought as insufficient water to meet needs, and this sort of covers a lot of the basis of drought. And of course, we had the big snow drought in the water year of 2014, 2015, and the narrative for that drought is we had pretty normal precipitation throughout the winter, right? Pretty much on par. Temperatures were way above normal. Snow levels were 1,000, 1,500 feet above normal. And what that resulted in was, near record low or record low April 1st snow water equivalent for a number of sites across the Northwest in spite of normal precipitation. And the reason for the Northwest snow drought was primarily due to natural variability. We had this thing called the blob, right, which is basically this area of anomalously warm water off the coast. But we also know that human-caused climate change, right, contributed to that. So human-caused climate change probably contributed to an additional 1 to 1.5 degrees Celsius worth of that warming that we saw. And the impact of the 2015 drought, of course, didn't end on April 1st with our low snowpack, as much of that precipitation fell as rain rather than snow, melted early. There was simply less water running off in the summer months. And so we saw our region's rivers turn into creeks and creeks turn into puddles. We saw the big sockeye die off in the Columbia. And then we saw the impending threat across the region's forests. Public lands were closed in Washington and much of northern Idaho just before July 4th. That didn't matter much. Lightning came without sufficient precipitation. And Washington state saw its largest fire season in terms of burned area in the observational record, and air quality and overall sort of quality of life was dismal at the end of August. It's the time of the year when we typically enjoy being outdoors in the Northwest. So how might climate change the odds of drought, right? So drought occurs naturally due to natural climate variability. One way that climate change might alter the odds of drought is by changes in the means, right? So more precipitation in the winter, that actually might decrease the odds of drought as defined by a precipitation drought in winter, right? But if we think about droughts like the 2014-2015 drought characterized by low snowpack and low stream flows and just incredibly dry conditions by midsummer that impacts irrigators, that impacts ecosystems, those sorts of droughts actually are likely to increase under future climate, right? Warmer temperatures overall increase the atmospheric water demand. They increase the potential evapotranspiration, right, which basically leaves vegetation thirstier, removes water from the streams themselves. And one other thing that you probably haven't heard much about with climate change, usually we talk about climate change in terms of means. Climate change can also influence the variability, right? So droughts are basically variability. And a study that David Root, Phil Mote, and I published a few months ago, we actually looked at this question. And what we found was that the models are suggestive of increases in precipitation variability in the summer and fall. And that by itself is going to increase the odds of drought. So let's take a look at this. Here's the Palmer Drought Severity Index in August of 2015. This is basically a normalized measure of soil moisture. The negative values less than -3 would indicate a severe drought. That's what we had. Question is, how much more frequent will droughts like this, at least viewed through the Palmer Drought Severity, be under climate change? And the answer to that, I did this using a number of different climate models. The answer is a lot more likely, right? So more or less on average across the Northwest, droughts of this magnitude, at least viewed through this particular lens, drought index lens, 3 times as likely. You could see some variability in there, right? And that has to do with the water holding capacity of the soils in the Columbia Basin and a bit more precipitation expressed as a percent across the basin there. But one of the uncertainties, right, one of these knowledge gaps that I mentioned earlier with drought is as we see climate change, and that's associated with increases in carbon dioxide, plants may become more water efficient in terms of how they utilize water. And so it's not 100% clear how droughts are really going to respond in the future due to the dynamics of vegetation. And so that actually may buffer some of these impacts. Okay, and then the final impact that I'll mention today is the premise of climate change influencing the frequency or intensity of bouts of heavy precipitation. Okay, and in the Northwest we have heavy precipitation. Predominantly, if you're on the west side of the Cascades, atmospheric rivers or Pineapple Express events are your primary culprit for heavy precipitation events. And it turns out that actually across much of the flanks of the northern Rockies, the same thing is the case. So how might the occurrence of heavy precipitation change in a changing climate? One thing we actually know is that as we warm the climate up globally, we see an increase in precipitation. So a warmer climate is a wetter climate globally, right? This says nothing about the spatial variability or geographic variability. And you get about a 2% increase in precipitation globally for every 1 degree Celsius rise in temperature. Okay? But if you look at the extremes, it turns out that the extremes increase at a much greater rate than the overall means. And so what we see across the mid-latitudes, and we're in the mid-latitudes here, is that for every 1 degree Celsius warming climate, we should expect, on average, and this doesn't account for spatial variability, but about a 6% increase in the magnitude of extreme precipitation. So the idea here is that the extremes increase at the expense of sort of the lighter events. We see larger precipitation, more of your overall precipitation occurring in extremes. And that applies to both daily extremes, multi-day extremes, as well as hourly extremes that might have impacts for urban flooding. Okay, and this is just one figure here showing the frequency of particularly heavy single or hourly precipitation events under the future climate, where you see about 150% increase across the Northwest and in the Northwest, in the Northwest, yeah. And another thing, of course, is we want to think about the drivers of these heavy precipitation events, and that's things like atmospheric rivers. So one question to ask is how atmospheric rivers may change in a changing climate. Most of the studies suggest that they will also increase in their frequency due to the fact that the atmosphere can hold more moisture. So I'll end there and basically conclude with reminding us that the Northwest is not immune to climate impacts and drought. And that the future tells us quite a bit. The science tells us quite a bit about the future. We don't know everything. We're trying to learn more about it. But the picture is rather clear. And we have a warmer future ahead of us. We have a future where water resources may become a little bit more volatile. And it's upon us to try to understand what we can from the science available today to adapt to what we have coming down the pipeline. So I'll end there, and if there's time for a couple questions, to take those.
Thanks, John.
On that second last slide, the possibility of heavier rain appears to be larger in the northern latitudes. Why would that be? My intuition was that it would be more in the more tropical latitudes. Why are you showing more in the north?
So one caveat in this particular figure here. This is from one model. Right, and so this is sort of the caveat of rather than look at a single model and draw conclusions, it's probably good to use a collection of models. This was one particular model where they actually had hourly resolution. But back to your question here, globally, it turns out that the largest overall increases in precipitation, expressed as a percent change, are expected to occur at high latitudes, and you end up seeing also increases in the tropics. And then between the two, in latitudes that tend to be a bit further south in the Northwest, places around 30 degrees latitude or so, you end up seeing a drying signal. So there are some reasons associated with that due to the dynamics where the jet stream is going to move up or north or south, and then the overall water holding capacity of the atmosphere.
Great talk. I was wondering if you would mention or compare the variability between precipitation that you see. You said it's pretty high, or that the variability may be increasing. How does that compare to the variability in temperature? And are the variability between temperature and precipitation different at different times of the year?
Good question, yeah. So it's been really cold, right? And it's tempting to attribute the anomalous cold that we've had recently with climate change. It turns out that the models at least tell us in terms of temperature that we should actually experience a reduction in temperature variability in the winter. And basically the reason for that is, think about where the really cold air comes from in the wintertime. It comes from interior Canada. And the rates of warming in the wintertime are expected to be much greater in Canada than they are here. So the source region for our cold air is warming at a faster rate than it is here. So temperature variability in winter is expected to actually be compressed a bit. In summer, actually the opposite. So we looked at this for summer, and it turns out that we see a bit larger spread in temperature variability in summer. And that has to do with the fact that as we talk about the hydrology, we see more precipitation falling as rain rather than snow, snowpack not being there, soil moisture declining, and we know that if we actually apply equal amounts of heat on dry soil versus wet soil, that dry soil is going to actually warm things up much greater. So greater temperature variability in the summertime associated with the dry soil. And that also does correspond with the increases in precipitation variability in the summertime. In the summer.
Does that mean more heat spikes in the summer?
We didn't look at, so variability can be expressed in different ways. The way that we looked at it was the year-to-year variability. So you could also think about variability as within a particular season, more volatile. And that's a very useful question, might be particularly useful for agriculture, but we didn't look at that explicitly.
You gave information on the changes in frequency of droughts and heavy precipitation events. Is there any information or enough to put some bounds on the uncertainty in terms of severity of these, both the drought and the heavy precipitation events?
Yeah, that's a good question, right? So what I presented today was sort of generalized, and it is useful to think about what sort of uncertainty is out there. It turns out that if you look at the sort of the model agreement on changes in precipitation intensity, they're actually in much greater agreement that precipitation intensity is going to increase versus the overall means. So from that perspective, they're telling us a pretty clear signature. Now, one thing that's, of course, of interest is if you think about how these models are projecting increases in precipitation and you want to figure out what that means at a local spot on the landscape, the results could be a little different, right? So it has to do with the dynamics of exactly what is responsible for the heavy precipitation in your particular area. If it's something like atmospheric rivers, probably we have a bit more confidence with that. If it's something like, rogue convective storms, that might be a bit more uncertain. When it comes to drought, we can certainly look at a metric like the standard drought indices and look at how it varies across models. And that's something that is probably fairly straightforward to do. And that would allow us to look at sort of the bounds. I showed you here just the average across those models, but then you could get an idea of where things fall. So those things are doable.
Any more questions for John?
So we're talking about variability, and there's also, if you watch the news, there's variation in also scientific opinion. So are there credible, in your opinion, credible scientists that think that global warming is not going to happen, that are actually studying this? I just wanted, you're in this area and know, everybody, this is hotly debated. I want your opinion,
One definition of credible has a lot of uncertainty to it and personal bias. But that being said, there's a giant prize out there for a scientist who can show that climate change is not due to increases in greenhouse gases. That prize is out there. It's been out there for decades. Still waiting, right? It's possible. Somebody could actually propose that hypothesis, test it out, and if it meets the merits of scientific, studies, then it comes into being a valid. And there are people that are doing this. There are a number of scientists who are looking at. I think there is a valid argument to make. We don't particularly know just how much the globe is going to warm if we double carbon dioxide concentrations. It's something called climate sensitivity, right? And so there's some good arguments to suggest that maybe the amount of warming that we're going to experience globally is, less than what the models are projecting. Could also be more. And so that sort of field of sort of scientific inquiry might fall into the skeptical camp, but they're probably more skeptical about the rates of change, right, and the resilience of the climate system as a whole. And then there are a lot of people also who like to, look at observations and, downplay them to some degree. So I think there are some credible scientists out there that are proposing hypotheses that might be against sort of what the conventional wisdom is. And that's healthy and good to some degree. To some degree, yeah.
Well, I just wanted to follow up on that question. I recently read what I thought was a brilliant book called Wine, Terroir, and Climate Change by John Gladstones. And it's a very technical book, spends about half of it talking about climate change, and argues that a lot of the research done to date is really flawed, really suggests that it's more earthly cycles than it is man-made climate change. But then at the end of the book comes the conclusion that man-made climate change is now taking over and is what will influence our weather patterns over the next century anyway. And very similar to the slide you showed, that 2050 is really kind of a breakpoint where, hey, from this point on, it's man-made and it's really significant. And I thought it was a really good job of addressing a lot of the naysayers in climate change, saying, hey, maybe a lot of the stuff to date isn't man-made climate change, but it's real on the global scale.
Mm-hmm. Yeah, that's a good point. Variability is always out there. Most of us have a selective memory for climate. It's difficult for us to perceive changes. We tend to notice a particular year, specifically the most recent, what's happening right now. And variability plays a role, right? Especially at regional scales in terms of the rates of changes, especially for things like precipitation.